Welcome to CrystalMaker 11. This tutorial introduces you to the Phonons Explorer, which we added in CrystalMaker 11. A crystal structure can be viewed as a system of springs connecting atoms in space, with the springs' force constants derived from interatomic potentials. We use these to compute vibrational modes throughout reciprocal space. These are traveling waves called phonons. We can visualize the atomic displacements for any given phonon in the same way that we can visualize atomic motions in a molecule. We can also visualize how the frequency of a phonon varies with its wavelength. This variation is called dispersion, and CrystalMaker lets you plot a set of dispersion curves between any 2 points in reciprocal space. CrystalMaker 11's new Phonons Explorer lets you choose a set of dispersion curves and then visualize the vibrations associated with a particular point on a particular curve. Let's take the mineral halite as an example. Here's the crystal structure. Now, before we start, it's vital that our structure be fully relaxed. Otherwise, you might observe negative frequencies for any simulated phonons. Halite is shown with a face-centered cubic structure, 4 lattice points per unit cell. The motif, that is the atoms associated with each lattice point, comprises 2 atoms, 1 sodium and 1 chlorine. So a primitive unit cell would have 2 atoms in it. Hence, we would expect a total of 3n equals 6 vibrational modes. Let's open up our Vibrations Explorer, and we can get there using the Simulate Phonons command, or if you've added the button to your toolbar, by clicking the Phonons button. This new window shows a set of dispersion curves on the left and an animation on the right. We can resize either pane by clicking and dragging the vertical separator. We'll start with the dispersion curves on the left. Click anywhere to stop the animation, and this reveals a set of color-coded dispersion curves. This graph plots vibrational frequency on the left-hand axis against wave vector, i.e. points in reciprocal space, on the x-axis. Now we can set the frequency units using the Units button in the toolbar. And we can specify the range of wave vectors along the x-axis by editing the start point and the end point for our axis. This is effectively a trajectory in reciprocal space. Now, by default, we are going from the origin of reciprocal space, or the gamma point, to a point halfway up the reciprocal z-axis. We can change this by editing the text fields or using the presets, such as this. The dispersion curves are updated and we get a new animation on the right. We can animate a phonon at a particular wave vector by clicking its point in the dispersion curve. The dispersion curve becomes highlighted and the other curves are grayed out. So here we see an optic mode involving opposite motions of the positive sodium ions and the negative chlorine ions. Now you may be asking at this stage why we're only seeing 4 curves and not the 6 that we expected. Well, it turns out that some of the modes have the same frequencies, and so their dispersion curves are superimposed. And we can demonstrate this by clicking on the lowest frequency mode and then using the pair up-down buttons to navigate all modes at the same wave vector. I'll keep clicking this button until it beeps, and then I know I've reached the bottom of our Phonons list. Now watch the animation as we move up through our stack of dispersion curves at this constant wave vector of approximately 0.5. Let's count the modes as we go. So this is our first mode, and this is a transverse acoustic mode. Mode 2, this is also a transverse acoustic mode, but if we were to rotate the structure, we'll see that the vibrations are at 90 degrees to the first mode. Clicking again. This is our third mode, and this is a longitudinal acoustic mode. Mode 4, this is an optical mode. The positive and negative ions are moving in opposite directions, and the frequency doesn't go to 0 at any point. Mode 5, another optic mode, same frequencies as before. And mode 6, our third optical mode. Just to be sure, let's click the up button and it beeps, so we've reached the end of our sequence. So that was a total of 6 dispersion curves. Now moving across to the animation pane on the right, we can rotate the structure by clicking and dragging with the mouse and see the animation in any direction. You can also scale by using standard multi-touch commands on all gestures on your trackpad, such as pinch or expand gestures. And we can set an explicit view direction using the axis popover. You can use the model menu to change the model type. And we could even switch to a 3D display mode. Use the animation popover to speed up the animation and change the amplitudes. And you can use the frame setting to generate a higher quality animation. We can export the animation as a movie using the output menu. We can actually export all details of all displayed phonons, that is their eigenvectors and eigenvalues, using the vibrations data command. And that will save a text file. Here we can see all points on all dispersion curves with their wave vectors, frequencies, and eigenvalues. Now, a note about these eigenvectors: each line represents one atom in the conventional unit cell. 1, 2, 3, 4, 5, 6, 7, 8 in our face-centered cubic unit cell with 4 lattice points per unit cell and a motif consisting of 1 sodium and 1 chlorine, 8 atoms. Each line has the real and imaginary components of the eigenvector. So we've seen how we can simulate phonons for any crystal structure. display sets of dispersion curves, then visualize the corresponding atomic displacements. These motions can be exported to a video file or summarized in a text file.